this video, we want to focus on Gibbs free energy and work, and specifically thinking about what do we mean by work? Is it work being done by the reaction, or is it work being done by the surroundings, and we're using Gibbs free energy to describe that? And so hopefully by the end of this video, we'll be able to describe Gibbs free energy, what we mean by it being called free energy, like why do we call it free energy? And then being able to distinguish conceptually between the work actually done by a reaction, by expansion, versus the amount of energy available for work to the surroundings. And then we're going to see that's going to be related to our Gibbs free energy change. So let's go ahead and lay a couple groundwork ideas forward, and then we'll go ahead and apply this in some examples. So first we want to look at what the change in Gibbs free energy is for reaction and why we call it free energy. So the Gibbs free energy change is equal to, for reaction, the amount of energy available for useful work to the surroundings. So effectively what we can say is the Gibbs free energy change for our reaction is equal and opposite to the Gibbs free energy change of the surroundings. So if we're giving away a negative delta G of the reaction, the surroundings is gaining that much energy that it can do something with it, right? And again, what can it do? Like, what is the surroundings going to be doing? It can be something where we move ions in an ion channel in maybe a biological system. It could be along the lines of looking at a reaction, how it corresponds to powering maybe a fuel cell that we would see for a specific type of reaction. So let's go ahead and look at it for this specific reaction. We have water being formed from hydrogen and oxygen gas. And we know the Gibbs free energy change is negative 474.4 kilojoules. Now what does that mean? What that means is that I would have a Gibbs free energy change for my reaction of negative 474.4 kilojoules for the reaction of 2 moles of H2, or if we look at it through the lens of O2, 1 mole of O2 reacting here, or for the reaction of and production of 2 moles of water. So we see here that this is scaled to the amount, right? If I have, for example here, let's say I go ahead and I have 1 mole of H2, that would mean the Gibbs free energy change is going to be the opposite of that, is going to be, half of that, negative 237.2 kilojoules. Or if I have 6 moles of H2 that's reacting, that would mean that our Gibbs free energy change for the reaction is going to be negative 1423.2 kilojoules. And again, that's corresponding to the amounts that we would have. That's why we're looking at those amounts. Now, how does this relate to the surroundings? If we look at each of these, what we could say is if this is the delta G of the reaction, the delta G of the surroundings is positive 1423.2 kilojoules, or the surroundings has 1423.2 kilojoules of energy available to do work, so to do something with it, right? Because if the reaction is giving away that much free energy, again, that's with 6 moles of H2 reacting with enough oxygen to produce that amount of water and get rid of all that hydrogen, we would see that that's how much energy is available for work, which is a pretty significant amount. And the reason why we're calling it free is that once this reaction is done, the surroundings has the ability to harness that energy in some way. Now, how that is harnessed is, there's a myriad of different ways to think about that. But what we do know is that that is the maximum energy. It may be lost in some way, but we know that's the maximum amount of energy that's available to do work for this surroundings. Now that's looking at the surroundings using the energy to do some amount of work. Now let's maybe contrast that to looking at expansion work for a reaction. And the expansion work is the work actually done by the system, the reaction, when it expands or contracts, when something's doing work on it. looking at constant pressure. So we see here, this is where work, depending on whether our reaction expands or contracts, it's going to either lose energy in the form of work or gain energy in the form of work by the surroundings on it. Now we can quantify this here if we're thinking about applying basically the ideal gas law and how that relates to our delta V. Okay, so we're not going to go through the derivation here, but we'll see is that the work for the reaction is equal to the change in number of moles of gas. And the reason why we're thinking of gas particles, because this was derived from the ideal gas law. In addition to that, the volume of gases are much larger, if we're thinking about the same amount, same number of moles, than a liquid or a solid. So again, we would say that we have a larger volume for the gases, and that's because if we're looking at, for a gas, if for example I have 1 mole of water as a liquid, that's going to be maybe something like 18 milliliters, whereas if I have 1 mole of water as a gas, and maybe at like our normal standard temperature and pressure, I'm going to have 22.4 liters. So not milliliters, but liters. We have an exorbitantly larger amount of volume for gases, and this is why we're focusing on the change in volume for a reaction here is primarily caused by gases being formed or gases being consumed. So a change in volume for the reaction is caused by consuming or producing gas particles. So let's look at our reaction here, and let's calculate what the work for the reaction would be. So the work for our reaction would be negative change in number of moles of gas times R times T. So that's going to be equal to negative. We have 0 moles of gas particles for our products, and it's always final minus initial, minus, I have 2 plus 1 more, 3 moles of gas particles for our reactants, and that's going to be multiplied by our R value, 8.314 joules per mole Kelvin. And we'll notice this is maybe different than the normal R value we use for like the ideal gas law, and all that's happened is we've converted liters, atmospheres to joules. So there's a connection there between work and energy. And so we have R and then times temperature here, 323.2 Kelvin. Again, we just converted that 50 degrees Celsius to Kelvin. And a way that remind us that this needs to be in Kelvin is that we notice here that our R value includes that temperature in Kelvin. So we would get the work for our reaction here to be equal to 8,060 joules per mole, or maybe if we want to put it along the same lines of energy that we would see for our free energy, so our delta G, we could also say this is 8.06 kilojoules per mole. So much smaller. So we notice we have, that's the amount of work done when it expands, so 8 kilojoules versus the 474 kilojoules released in the form of Gibbs free energy. And again, this is the work or energy released when it expands actually done when the reaction expands. And we contrast that to delta G, which delta G is thinking about the free energy available to the surroundings by utilizing that free energy being given away. So that's the surroundings has the ability to do work based upon using that energy in some way. So now that we had a chance to look at those ideas, why don't you go ahead and pause and practice here. So we have this overall reaction, and we have some information about the change in enthalpy and the change in entropy for this reaction. And we're going to look at 2 possible ways that this reaction can be utilized. And this is the oxidation or also combustion of ethanol. And it can be used in a fuel cell. And in the fuel cell uses the free energy and converts it to electrical energy, which powers electric motors. Whereas if we look at it in a combustion energy, it expands if we think about how combustion energy works. So what we're going to do is we're going to compare A and B, the amount of energy released or available for work for a fuel cell versus the amount of energy or work actually done when the reaction occurs in a combustion energy. So why don't you go ahead and pause the video and answer this question on your own, and then come back and see how I thought through it. All right, so the first thing that we wanted to do is that we want to actually calculate the delta G of the reaction. And for us to do that based upon how this reaction is actually written out, because this delta H and this delta S corresponds to 1 mole of ethanol, 3 moles of oxygen, 2 moles of carbon dioxide, and 3 moles of water. And then we're going to connect that to 15 kilograms of ethanol actually being used in this fuel cell. So here we have the delta G equals delta H minus T delta S. Because we knew delta H and delta S, we have the ability to calculate our delta G. So our delta G for the reaction is going to be our delta H, negative 1,234.77 kilojoules, minus the temperature we're at, 125 degrees Celsius, or 398 Kelvin. We have our delta S. And again, we notice here delta S is in joules, our delta H is in kilojoules. So we want to make sure that those match up. So we're going to go ahead and convert that to kilojoules, which would be 0.2173 kilojoules per Kelvin. And so we would find that our delta G for our reaction is negative 1,321.26 kilojoules. Now that's the kilojoules, the amount of free energy. And because we're looking at ethanol here, for the reaction of 1 mole of ethanol. So now we have the ability to connect this maybe back to our amount that we have, 15 kilograms of ethanol. So if we want to do that, we first want to find the delta G for 15 kilograms of ethanol. Well, that's going to be, let's start with our amount of ethanol that we have, because we want to scale that to the amount that we would have for 1 mole. So we have 15,000 grams of ethanol. And before we can do anything, we need to connect that to the number of moles. So let's go ahead and convert that to the number of moles using our molar mass, 46.07 grams of ethanol per mole. And now we have this conversion factor effectively of free energy per the amount, 1 mole. So I'm going to have a conversion factor of negative 1,321.26 kilojoules. That's our delta G for 1 mole, the amount that we actually reacted when we calculated that delta G. So this is our delta G being used as a conversion factor to scale it to the amount that we actually reacted. And we would get negative 4.302 times 10 to the 5th kilojoules. Now, what does that mean? The maximum energy available for work for the surroundings. Well, that also tells us that we would have, because our delta G of the reaction is equal and opposite to the delta G of the surroundings, we have positive 4.302 times 10 to the 5th kilojoules available to the surroundings to do work, in this case power maybe the electric motors in the fuel cell, from the fuel cell. Now we have that's identified with regards to free energy. Now in our next one, what we're doing is we're being asked to think, if this reaction were used in a combustion engine, what amount of expansion work would be done by the system or the reaction? So we're actually looking at expansion work. And anytime we see this, we may think we see work, we think delta G. But again, here we're looking at expansion work, and that would mean the work the reaction does is negative change in number of moles of gas times R times T. And again, we're going to scale it to the 15 kilograms of ethanol at 125 degrees Celsius. So let's look at, in a combustion engine, it's going to push against those pistons, and it's going to cause the volume to expand. So now if we're going to calculate our work, let's start by looking at the amounts that we have in our balanced chemical equation to quantify this. So it's going to be negative change number of moles of gas. So we would see we have 2 moles and another 3. So we have 5 moles of gas particles as our product, so final. And we have 0, this is a liquid, plus another 3. So we would minus 3 moles of gas particles for our reactants. So that tells us something about the change in moles of gas. So we notice it's going from a smaller to a larger, so the volume is going to expand. It's going to use energy. It's going to lose energy when it does that. Our R value, 8.314 joules per mole Kelvin, and our temperature here, 398 Kelvin. We'll go ahead and plug that in to our calculator, and we're going to get negative 6,618 joules per mole. And that's going to be for the amount that we have for ethanol here, 1 mole of ethanol. Now again, we want to scale this to the 15 kilograms. So if we want to look at the work for 15 kilograms, that's going to be 15,000 grams. And again, we have this in a molar amount. So let's go ahead and first convert it to moles. 1 mole of ethanol, we would see for 46.07 grams. This is our molar mass. And then we would have 1 mole of ethanol that we'd have here. And that's going to correspond to the number of joules of work that was done. We could also, if we wanted to convert that to kilojoules, which would be negative 6.618 kilojoules per mole that we would see there. And the reason why we maybe would want to do that is that we're going to be able to compare it to our work for the delta G. And so we would get a value of negative 2,155 kilojoules of work done by the reaction by expansion. And so we'll notice that this reaction cannot do that much work because it's just expanding. It's losing a lot of energy as it's expanding. And we'll see here that we compare this to the free energy change. We notice that our free energy change for our reaction was negative 4.302 times 10 to the 5th kilojoules. So that's much larger for this reaction. And we'll see that that is going to release a lot more energy. So this hopefully gives us a distinction between work actually done by reaction versus maximum energy available to do work for the surroundings as free energy is given away.